AUTOSAR. Explained by Annette Kempf.
Hello, thank you for joining again for another session on AUTOSAR. We are looking at AUTOSAR Classic Platform, and within the AUTOSAR Classic Platform, we will have a look at Microcontroller Abstraction Layer, and in detail, we will have a look at the memory drivers. But first of all, we'll start with a look at where we are in the structure, how the overall AUTOSAR is structured, where the microcontroller abstraction layer is, and so on. And once we have this introduction, we will have a look at the different specification, navigate through the website first and to different specifications which are part of the memory drivers, so that you have a navigation and the detail. So first start now with e-learning course on AUTOSAR Classic, which is providing you with an introduction, and then I will be right back. See you.
The Classic Platform is AUTOSAR's solution for embedded systems with hard real-time and safety constraints. The architecture distinguishes on the highest abstraction level between three software layers which run on a microcontroller. The lowest layer is the basic software layer. It is divided into three major layers and complex drivers. The Microcontroller Abstraction Layer is the lowest software layer of the basic software. It contains internal drivers, which are software modules with direct access to peripherals. The main task of this layer is to make higher software layers independent of microcontrollers. The ECU abstraction layer connects the drivers of the microcontroller abstraction layer. It also contains drivers for external devices. It offers an application interface for access to peripherals and devices regardless of their location and their connection to the microcontroller. The main task of this layer is to make higher software layers independent of the ECU hardware layout. The complex drivers layer spans from the hardware to the runtime environment. Its main task is to provide the possibility to integrate special-purpose functionality. The services layer is the highest layer of the basic software, which also applies for its relevance for the application software. It offers, for example, diagnostic services and memory services. Its main task is to provide basic services for applications, runtime environment and basic software modules. Above the basic software lays the runtime environment. This layer provides communication services to the application software. The AUTOSAR software components communicate with other components and services via the runtime environment. The main task of this layer is to make the AUTOSAR software components independent from the mapping to a specific ECU. The application software layer realizes the application functionality. This layer is mostly hardware independent and consists of different software components. The microcontroller abstraction layer is divided into 6 model groups, which group software modules of similar type. In this case, the software modules are internal drivers. A driver is a software module with direct access to peripherals. The internal peripheral devices are shown in the hard. The module group memory drivers consists of drivers for memory-mapped external memory devices, like the external flash, and on-chip memory devices, like the internal flash and the internal EEPROM.
So I hope you enjoyed this introduction on the microcontroller abstraction layer, and now we will have a look at the memory drivers. So we are here now at the Classic Platform AUTOSAR webpage, and looking at the current release, which is 11.23. So from last year in November, and there will be a new release this November again, like every year. Yeah. And we have now here the overall picture. The microcontroller is not part of AUTOSAR, it's the hardware in itself. We had a look before at the microcontroller drivers, and now we'll have a look at the memory drivers. So going there on the memory drivers. It's the crypto drivers. I'll go back. I'm clicking on memory drivers and I get the crypto drivers. So some big bug fix needs to be done by AUTOSAR. Here you have a release, so you can choose between different releases. We have here the classic platform, and we have the architecture element. So the memory drivers are called architecture element, and this one is wrong because it's crypto drivers. So we now have to look at the memory drivers. There are two. I take the second one. First one says it's a different filter. So, and here it says it's the filter of a actual revision. So we'll choose this one. And now in our selection, okay, now you see you can also select different architecture elements to get more specifications. But this is not what we want today. So we'll remove the crypto drivers. And now finally we got to the list of the memory drivers. And there you see it's a mixture of explanation, handling guideline, requirement, and specification. And it's quite a lot of specification. You always have the requirements separate and then the specifications of the different drivers. So I would say this explanation for firmware over the air update, it's like a additional guidance if you need to do this. And the same for NV data handling. Non-volatile data memory is NV. So we'll start this with specifications. And you see it's quite a lot of specifications for the memory driver, addressing like different parts of memory. I would now start with a specification of a EEPROM driver. It's for old stuff, yeah. Even in 8051 microcontroller, you had EEPROM. So here it's introduction and functional overview. So it's, of course, describing the functionality for EEPROMs. And for EEPROM, what you're doing with it is you read, you write, or you erase the memory, and so that you can write again, yeah? And for EEPROM, erasing the memory usually is not that easy. And it's also providing the services for comparing a data block with data block in RAM. Because if you erase something, you would have to put also the data somewhere before flashing new, writing to it. Yeah? And the EEPROM is a part of a microcontroller abstraction layer. And I would say that it's a part where you are rarely in contact with, because usually I would say it's part of what you get from the microcontroller, except that it's an external EEPROM device which you need to access. Yeah? So maybe here it's important to know that an EEPROM driver is not providing data integrity like checksum, redundant storage, and so on. All the details, I would say, on the handling you can read, but there's one topic which is very, very important, which most likely you find in not so many specifications and only maybe in the hardware specification of the EEPROM. Usually you cannot write an infinitive number of writing cycles like deleting and flashing again on an EEPROM, but it's limited. So you have the hardware restrictions, and these hardware restrictions are very, very important. And I can tell you, if you choose the recurrence of deleting and writing too often, then you can sit down and calculate and find out, okay, the ECU of my whatever I'm doing in the vehicle will break at the customer side after 3 to 5 years, depending on how much they are driving. And this is something you don't want to do. So you really have to think about, in terms of concepts, on how often you are erasing data there and writing new. I would say this is the most important thing to know about EEPROM. Yeah? Then we'll have a look at the next. It's the flash test. Yeah. We had the core test, and now we also before last week in the microcontroller drivers, and now we have the flash test for the flash. It's always a long way to get to the core of a specification. It's the flash test driver. And this module provides an algorithm to test invariable memory. So it can be data or the program, the SRAM also. It can be locked cache and either embedded in the microcontroller or memory connected to the microcontroller, meaning that you have an external memory which is on your ECU board, but not a part of a microcontroller. And to find a simple name, it was called flash test driver. So the test services can be executed anytime after MCU initialization. So you can have it also running, for example, in the background. And the test service itself is dependent on the storage concept of the system. Yeah? And there are different test algorithms which are possible. So it's always a lot of scrolling until you get to the real functionality. And this is the functional specification. So you have different execution services. Yeah. And as I said before, shall be configurable for background and foreground. So you can also run your test, especially on the flash, in the background when the microcontroller is idle. Yeah. And here you see, for example, a scheduling interval as an example. And background test process. For a state diagram, you always have the different states of the drivers. And this is the state diagram for the background mode. So it's tested in background. I'm just scrolling to have, I'm not sure if we should go into that much detail, yeah, because I think whatever functionality you need to test your flash, you need to have a look at what you actually need in this case, so that you can choose the right functionality, because it's now 55 pages. I think it's too much. But again, think about how you're testing it, background, foreground, so that you ensure that the test is done in time. So this is the part of a flash test. You have a flash driver. We also have a RAM test. We have memory mapping, we have memory access, and we have a memory driver. So the next driver is the flash driver in the list. And it's interesting, normally it's alphabetically ordered. Here it's not the case. So we have a look at the flash driver. What does the flash driver do? First of all, it's addressing external flash memory and internal flash memory, so both, yeah. And it's similar to the EEPROM. So you have reading, writing, and erasing flash memory. And often, if you don't have an EEPROM, certain flash sections are used to represent EEPROM functionality. For the flash, the same applies, as I said, for EEPROM, yeah. Because you cannot write and erase whatever often you want, yeah. You have to check your hardware manual how many cycles to rewrite the memory you have, as that it's guaranteed that it's still working. Like I said, in a certain application mode of the ECU, the flash driver is only to be used by the flash EEPROM emulation module for writing data. It is not intended to write program code to flash memory in application mode. So anyway, it doesn't make sense to write so often because then your hardware will break. A driver of an internal flash memory accesses the microcontroller hardware directly. And as a functionality, like I said, it's part of the memory drivers within the microcontroller abstraction layer. An external flash memory is usually connected via the microcontroller buses, yeah. Could be, for example, that you have a chip select and an SPI connection, just as an example. And then also you can have like all the lines connected with several pins. The flash driver then uses the handlers and drivers for those buses and external flash memory device, yeah. And to access the external, you also need to have the ECU abstraction layer. So we are now talking about the microcontroller abstraction layer. It's really all the connections and so on. But then there's also a level above, which is doing this abstraction, because what you want to have, if you're running the normal application software, you don't want the guys who are working on, for example, control algorithms, that they have to think about if it's in the external or internal flash memory. This has to be abstracted, and it's just a memory access. Yeah. So this is the target of the flash driver. Then we have the specification of a RAM test. So this is also part of a memory driver's RAM test. And RAM, in comparison to ROM, is very dynamic, because you read and write all the time, and you have many more writing cycles there. It's completely different topics. Yeah. So the RAM test is not like looking, I expect this to be in the memory and I'm checking it. It's testing for the physical health of our RAM cells. So they have to work in all conditions, yeah, and they have to keep the data. so this is the target to say I'm testing for the physical health. Yeah. So RAM cells are a unit of memory which can be individually accessed by the processor. So cell size in bits, if you have a 16-bit microcontroller processor, it's 16-bit. And there are different algorithms to test the RAM. They are targeted to test different sets of fault modes, which then achieve a different coverage and result in different run times. And you can do destructive or non-destructive testing. So you can either override the RAM cells or you can read them. Yeah. And of course, the coverage depends on the underlying physical RAM architecture. Within here now, the ISO 26262 is mentioned. The ISO 26262 is the standard for functional safety, and it also specifies certain requirements, and there are it's distinguishing between 3 basic coverage levels. It's low 60%, medium 90%, and high 99%. And this distinction was taken over and is used also in exactly this specification within AUTOSAR. So the ECU safety analysis. So then this is also connected to the functional safety level. Yeah, you need to define the coverage rate. Low, medium, and high is required according to this, depending on which functional safety level QM, ASIL A, B, C, or D you have. Appropriate RAM test algorithms for further configuration parameters then have to be selected at the compile time. So you select beforehand, and at runtime, this application software is choosing between these compiled algorithms and further parameters. This is how the functionality is done. You can have RAM test, which is called synchronously by the test environment. So this means that it's a foreground test and then called in a cyclic manner by the operating system or any other cyclic calling method. You can also do it in background. Yeah, the test environment may select test parameters, start and stop and test, and get status report. Concerning this background, doing RAM test in the background is really difficult because you need to ensure that the RAM is used. Otherwise, you can only check for reading. Yeah, when you have an idle task. Development errors are reported to the default error trace, DET, and production errors are reported to the diagnostic event manager, DEM. These we will have a look at later because they are not in the microcontroller abstraction layer, but in higher layers of the AUTOSAR architecture. Yeah? So the RAM test module consists of a RAM test main function for background testing, the APIs for foreground testing, and several configuration status APIs for several configuration parameters. But I think this is the point where you also are going into more details, and if you read thoroughly, you will know exactly what to do there. So I hope I gave enough orientation, covered these memory drivers. Then there are more specification on, now we finished all the testing part. Yeah. And now there are specification on all this memory handling, memory mapping, memory access, and memory driver. So memory mapping. Yeah, well, the disclaimer. So for memory mapping, you have to organize the memory, and it has different targets. So the usage, which memory is used for what, yeah. Also, you have, especially for the ROM, you have structures, you have checksums you're writing. So you have, and especially if you have external and internal memory, you have access times which are faster or slower. So you are going to optimize runtime via the distributing of these different memory areas to different functionalities. So it's really a topic you have to think about, yeah. And in this document, the mechanisms of mapping the code and data to specific memory sections via memory mapping files is described, yeah. So it's the doing, and with these different targets. So for example, avoidance of waste of RAM. So besides symbols with defined alignment, e.g. code, yeah, further symbols of different alignment, 6, for example, 8, 16, or 64-bit and size have to be allocated. This, and if unsorted, then the linker has to leave gaps, because you cannot start in the middle of nowhere with 64 bits. Yeah, you have a certain width of memory, and if it's not filled, then you count up. For example, you start then for the next 32 bits again. And if you have, for example, only 8-bit, and then the next one is 32-bit, then you will leave a gap. In this example, depends on the microcontroller, of 3 bits. And this is because, like I said, the microcontroller platform requires a specific alignment for symbols, and the linker usually does not offer an optimization on variable allocation. So this is one topic you can handle, to say you don't want to have gaps in the RAM. So to avoid the RAM waste, you have to align and structure the variables in a correct way. So you have a usage of specific RAM properties. So some variables, and also RAM mirrors. So sometimes you mirror the RAM, for example, into the non-volatile RAM manager, and these must be initialized after a non-cold power on reset. Yeah. So it's necessary, or shall be possible, to map them to the RAM section that is not initialized at any reset except cold power reset. This is just one example. Sorry, this is my mobile phone ringing right now, even if I put it to quiet. Then you have also usage of specific ROM properties. Yeah. Like I said before, if you have large ECUs where the internal flash memory is not sufficient, and you also need external flash memory in addition to that, yeah, then it is usually a requirement to map the modules with functions that are called very often, yeah, into the internal flash memory, and that, because this is allowing for faster access, and then you have a higher performance of your system, and less problems, for example, that you have a too high CPU load. To keep CPU load low, you need to look at your distribution of your functions within the ROM. And for functions which are called rarely, not so often, and have lower performance requirements, these can be mapped to the external flash memory that has a slower access. Yeah? So you see there is already quite a lot of topics to look at, how to distribute, how to initialize. So there is a lot of know-how also on your overall system, on the functionality, and usually this is highly connected to the operating system, that you have a look at your task, how fast they are called, and then to find the right mapping. So I saw companies in the past who have been writing tools on how to do the optimized mapping in addition to these drivers. Yeah. Then you have, of course, also some bootloader functions, applications. You have the functionality if you flash new to save the existing code, then to flash the new code, and if everything worked fine, delete the old code, flash the new code, and if everything worked fine, you can delete this backup you made. So this is things you need to do. For functional safety, you also have a topic that sometimes memory protection and partitioning is required, and this can also be handled via this way. Yeah. So this was the memory mapping. So you really have requirements from your system concerning memory mapping. Then two more specifications. I think it's getting long already. You have the memory access. Yeah. Again, we have to get to the driver. It's not that big. Yeah. Then here you have an introduction and the functional overview. So it's really this memory access is a very important interface. But it provides the access to the different memory technology devices by an address-based API. So you say, this is the memory address and I'm accessing it. And all the other things have to handle behind. The memory access module is always complemented by one or more memory drivers. The memory access module is memory device technology agnostic and can be used with typical memory devices such as the flash we saw before, EEPROM, RAM, or phase change memory. The memory access module and memory driver are located in the same layer of the AUTOSAR architecture as the flash and EEP driver, but split these modules into a hardware-independent part, MEM-ACC, and a hardware-dependent part, MEM. So you have it split up into different parts, which is not so easy to handle. Here you see it's the colors, provided as a memory architecture example. So now here we are leaving also the memory abstraction layer. These are part of the memory abstraction layer. This is part of the ECU abstraction layer, and this is part of the services layer. And if you look at here, you see exactly here the colors again. And you see here you have a memory drivers, and you have a memory hardware abstraction, and you have a memory services. And this is what we saw there with the colors. So you have this blue, green, and red color. Going back here, this is the representation. So what we are looking now at the memory drivers within the memory microcontroller abstraction layer, we are only looking at these red ones, which are specified. I would say, maybe we have another look at the use cases, but then I would close the meeting for today. The combination of memory access module and the MEM driver supports the following use cases. So it's like the combination you have to look at. Block-based non-volatile memory access for data storage using non-volatile memory, and FEE or EA. OTA over VR, software update, and general address-based memory access for BNDM or flash bootloader usage. And combinations are also supported. And since this MEM access module and the MEM driver also cover the flash and EEP use cases for non-volatile data storage, FLS and EEP become obsolete in the future. Okay, then this was memory access. We already talked about the memory driver. We'll just have a very short sneak peek, and then I would say we're done for today. Specification of a memory driver. Now we are getting faster in scrolling. Introduction and functional overview. You see it's the same picture. Yeah. Same picture as I explained, red, we are in the microcontroller abstraction layer, ECU abstraction layer, and services layer. The memory driver provides the basic services for accessing different kinds of memory devices like reading, writing, erasing, and blank checking. Also, flash memory is still the most common non-volatile memory technology. The memory driver specification considers all relevant memory device technologies like EEPROM, phase change memory, in short PCM, and ferroelectric RAM. To harmonize these memory access to the upper layers, the memory driver specification also covers access of RAM. So you have like the abstraction, and this is the target memory microcontroller abstraction layer with the memory drivers to usage on an application software. It's almost irrelevant, but it's not completely irrelevant because you have the hardware constraints, how often you're allowed to write to this hardware. In contrast to the flash and EEPROM driver specification, the memory driver specification explicitly covers also code memory access to support new use cases like background over VR update, which require code memory access. Yeah. So I would say for this, it has been long enough to look into the different part. So we looked into AUTOSAR Classic, microcontroller abstraction layer, and there the memory drivers. And next week we'll get to the next topic. Thank you for joining us, and I hope you enjoyed the explanations, and I hope to see you again. Thank you, and bye-bye.
If you want to learn more about AUTOSAR and other interesting topics, go to embedded-academy.com.